I'm going to talk to you about how we can solve ordinary differential equations using numerical methods. For reference, this comes from part 7, which is chapter 5 of our textbook, Numerical Methods for Engineers. And this chapter is called Runge-Kutta methods. And Runge-Kutta methods are a family of methods. There are multiple different types of methods, but they all solve a very similar type of ordinary differential equation. And we'll talk more about that. And today we're going to talk about one type of Runge-Kutta method, known as Euler's method. Now, I mentioned Runge-Kutta methods all solve differential equations of one form. The form that they solve is dy dx is equal to some function f of x comma y. So some function of x and y, given an initial condition y at some location, say x naught, is equal to some value y naught. So that's our differential equation and our initial condition. Now, this may look rather simplistic, but in reality, f can be a very complex function. It can be a complex function of x and y. It can be linear, nonlinear. The only thing that matters is we only have one derivative, and that's dy dx. So this is a first order ordinary differential equation, which is first order ODE. And these methods apply to any first order ODE. And the goal, just like what you might have done in your differential equations class, is to find the solution. More precisely, we're going to find the particular solution, which we can write as y as a function of x. That's the goal. Find y as a function of x for this differential equation. And to do that, we're going to leverage a fact that dy dx is a slope. And it is the change in y over the change in x. And the other key part of that is that this is known. And how is it known? Well, it's given by the differential equation. So if I look back at what we did, this equation up here gives us dy dx. So we know the slope as a function of x and y of our solution. So how can we use that? Well, let's look at an example. So I'm going to look at an example where we have our differential equation is going to be dy dx is equal to minus x plus 2, which, let's write that a little bit in a slightly different form. Let's just say that that is 2 minus x. That's our differential equation. Dy dx is 2 minus x. And we also have our initial condition, y at x is equal to 0 is given by 1. So we know that our solution goes through the point 0, 1. And with that, we want to find our solution. And I told you that dy dx is the slope. So this is the slope. And how can we use that to find the solution? Well, let's just look at our plot down here. And on this plot, we're going to find the solution. So how do we do that? Well, I told you we know a point. We already know a point. So let's start with that point. So at this location, x0, 1, we know our first point. So we know our solution goes through here. And we know that that point, y of 0 is equal to 1. And that's just our initial condition. And what is the slope there? Well, we can say that the slope is dy dx, which is equal to 2 minus x, just given by our original equation, which is equal to 2 minus 0, which is just 2. So we know our slope at this location is given by 2. And with that, we're going to draw a line with slope 2 that extends out from there. Here's our line. Has slope 2, and it goes right where we need it to go. So let me just mark this as having slope 2. Oops. And that now gives us a new point on our solution. So now we have a new point up here that is part of our solution. So we had 1 point, now we have 2 points. And this point is the point y of 1 is equal to 3. And it has slope dy dx is equal to 2 minus x, which is equal to 2 minus 1, which is equal to 1. So we know the slope here is equal to 1. And how can we use that to our advantage? Well, now we can extend our line even further with the slope is equal to 1. So I'm going to use that and move out and to the right. And we'll get another point on our solution. And this point has coordinates y of 2 is equal to 4. So now we have 3 points in our solution. And here we know the slope is equal to dy dx, which is equal to 2 minus x, and now we're at x is equal to 2, so this is just 2 minus 2, which is equal to 0. So now my slope at this point is 0, and I can use that to extend my solution even further. So I'm going to extend my solution out with a 0 slope over to that point. And then I have another point in my solution. At this point, I can figure out that my location is y of 3 is equal to 4. And my slope here is equal to 2 minus x, which is equal to minus 1. And if I use that, I can extend my solution one more time, back down to my final point out here. And now I have my solution. My solution goes up and down. And I've found 4 new points on my solution using this method. And this is what we call Euler's method. And let me just recap what we did. So we used the current point to find a slope. So we started at the initial condition, we found a slope there. Then we used that slope to find a new point. We went from point 1 to point 2. At the new point, we computed a new slope, and we repeated this process over and over again. And then if we do that, we find the solution to our differential equation. And this works for any differential equation. This was a rather simple differential equation, but we could have a very complex solution over here. So this differential equation could be much more complicated, and the same procedure would work. Remember, we're only limited to the fact that we need to have a first order ODE. Other than that, the solution technique will work for any first order ODE. In the next video, we'll give a more formal definition of Euler's method and apply it to another example and compare it to the analytic solution.